stated the main theorem with a corollary, so I thought I should restate that. So let me do that first. And I neglected to say last time that it is this result is a joint theorem with Luis Lomeli. Okay, so the theorem is given a bunch of data, then you can find some cuspidal representation with some properties. Okay? So the data that is given includes a global field, K, okay, but well, so I'm going to assume a positive characteristic. Okay, so it's the function field of an absolutely irreducible smooth projective curve over a finite field. Okay. So with pedals ring A. So here Y is a curve over a finite field. Okay. And I'm given S naught non-empty finite set of places of K, which is the same as saying that it is a finite set on the set of closed points of the curve Y. And I'm given a connected reductive group H over K. Let me denote its the center will be ZH, and then the identity component of the center will be Z. So it is a torus. I have N in H. A smooth connected K-split unipotent subgroup. So at the end of last time, I guess I give some examples to illustrate, that if you don't put this condition, especially K-split, you can have some rather nasty unipotent subgroups, and I want to avoid those. Okay, we have that. Then, in addition, you have chi. So this is a automorphic character of unitary character. Well, this is not a group, but okay. You have omega. It's basically a central character, so an automorphic central character. Assume it is unitary. So you see, so far all the data are global, right? You have some global field with some groups, algebraic groups defined over that global field K. You have a bunch of automorphic characters. Okay? And so here now you have the local data, which is for all V, for all places V in the finite set S naught. I'm given a pi V, which is a irreducible supercuspidal representation of HV. And such that basically it has central character omega V. But let me write it this way. Okay, and I'll call, so this condition is just, instead of having to write it down each time, I will say that this is saying that pi v is chi v distinguished. So that's the data that is given, and then the conclusion is that there exists a cuspidal automorphic representation pi of H A satisfying a bunch of conditions. So firstly, this pi globalizes the given supercuspidal. And for all v not in S0, I want to say that let me say that pi v is contained in the principal series. Okay, so it's contained in some induced representation tau v with p naught v minimal parabolic over AB. And in fact, I mean, more or less, you can say this guy has depth 0. Okay, it has very low ramification. But let me not emphasize that here. I mean, it's important for me to be like that. And finally, what has this got to do with chi? Well, and omega, well, it has central character omega, okay, meaning character under z. And lastly, pi is so-called globally anti-distinguished, which means that the map, if you take a function in pi and you write down this integral, so this is a linear function on pi, right? And in fact, it defines an element in the global analog of this Hom space, okay, where you suppress the V and you replace, you consider adelic groups. It is a certain explicitly constructed element in that Hom space, and we want this to be non-zero. Okay, so as I said, so today what I want to do for the first hour is to discuss the proof of this in some detail. Okay. Now, so for the purpose of the proof, of course, I'm going to just make life easier by going to assume my group H is split semi-simple. Okay. Then, of course, for every V, HV is split as well. So this E0V is just a Borel subgroup. And I'm going to also simplify my life here. So I assume N is any unipotent subgroup, right? But I'm going to simplify my life by considering sort of only two cases. One is N is trivial. That's the trivial group is an example, right? And the other example I'll keep in mind is when N is the unipotent radical of the Borel subgroup. Okay? In that case, I'm especially interested in the case when the character chi is a so-called character in general position, or a generic character. Okay? In that case, the condition here is saying that the supercuspidal are so-called generic supercuspidal, and this linear function is the so-called Whittaker Fourier coefficient. Okay, so these are, okay, so, but before going to the proof, let me just say so the proof basically relies on the following sort of baby observation. Okay? somehow a trivial observation. So let me describe this. So suppose you have the observation is the following. Suppose you have a number. Suppose you have an alpha, okay, an integer, okay, and for some reason, you know, it is in an interval like that. Let's say, okay. So how to show? So two ways to show that alpha is 0. Okay, of course, there might be more than two ways, but here are two ways. Okay, one is to show that alpha is divisible by p to the n for n very, very big. Okay, so if you could do that, so for example, if this p to the n is bigger than capital N, you know, then the only possibility is alpha equals to 0. But here's another way. Show that alpha is divisible by sufficiently many prime p's. If you can show that this integer, which you already know lies in some fixed interval, okay, is divisible by too many primes, then it had better be 0. Okay. Anyhow, okay, of course, this is a simple observation, but you will see as I describe the proof, you may try to see where this observation is used. Okay, now let's go into the proof of the theorem. Okay, so so proof of theorem. As I said, I'm going to assume that H. So I'm going to put some simplifying assumption. So it's split semi-simple, and let's say I have a Borel, okay? Borel K subgroup, and I'm going to assume that N is either trivial, okay, or the unipotent radical. Of B. Yeah, just keep these two cases in mind. In fact, for the applications that I will speak about from next time on, these two cases suffice. All right. So since H is split semi-simple, I can fix an embedding. Let's call it iota from H, close embedding to some SL n, okay, which of course is containing GLN. Okay, so in fact, you can even simplify your life further by just taking H to be SLN. So I think that's fine. Okay, so you can pretend this is an isomorphism. Okay, so in any case, and I'm thinking of GLN as really n by n matrices. Okay, so they are n square coordinate functions. Right? So from here, we are going to get coordinate functions xij on H. And of course, any point on H is determined by the value that these n square functions take. Right? If you give me a point on H, and if I know all the coordinates, then I know what that point is. Okay. All right. Now, so I want to pick this embedding in such a way, so without loss of generality, I may assume the following compatibility. Okay, so first, let me assume that I can put this H inside so that B intersect. So that this Borel subgroup is nothing but H intersect the upper triangular Borel of GLN. Okay, why not? Okay, you can assume that. So maybe this I call it T times U. Okay, so and you can assume T is just H intersect the diagonal matrices. Right? You can assume U is H intersect upper triangular unipotent. You can assume that H intersect lower triangular unipotent is the opposite. Is an opposite or unipotent radical. Okay, so this you can do that. So in fact, as I said, if you just take H to be SLN, then you don't even need this to mention this. Okay, and of course, I can assume that this N is contained in U, right? Because N is some unipotent subgroup, K split, and you can conjugate it so that it lives inside this specific maximal unipotent subgroup, U. Okay? That doesn't destroy those conditions over there. So you can assume that. So as I said, I'm going to consider only these two cases. Okay, so this is the case when it is just U. Okay, so these are all okay. All right. Now let me continue on that part. All right. So now we have a non-empty set S0, right? In the theorem. So okay. So if we let O S0 be the ring of S0 integers in K, so this means all the functions on Y, which are regular at outside this set. Okay, then of course we from this we are going to get a O S naught integral structure on GLN and hence H. All right, but I'm not sure why I say that. But so now let S be a large. Yeah. So I think that the reason I want to say that was just okay. So I'm just saying that you have GLN. It has the n entries, so you can n square entries. You just give it the naive OS not integral structure. Okay, and which then induces some integral structure on H. Right? So, but you see, if you then think of H as a group scheme over spec of OS naught, of course it could have bad reduction at many places. Okay, but that set of bad reduction is or anything bad that could happen will be concentrated in some finite set. So if you throw away some big finite set of places, everything will be nice, smooth, and ramified outside that finite set. And that's what I want to say here. Be a large finite set of places such that, well, so firstly, I assume it is different from naught. And for all V, everything is nice and smooth. So H is smooth reductive over OV. Okay, in other words, if you look at HOV, which is nothing but HK intersect GLN OV, okay, it is a so-called hyperspecial maximum compact subgroup. Okay. So outside some finite set, you'll be okay. Now, but I want to assume more. So I want to also say that if I look at, I'm going to define something called IV plus. And what is this? This is the intersection of HKV with the upper triangular Iwahori subgroup of GLN. Okay. Then this intersection is an Iwahori subgroup. Okay, of HKV. Okay, as I said, I mean, if you just take H to be SLN, then this is okay. Right? But in general, the point is that if this guy is a hyperspecial, and if you look at the reduction mod pi v, okay, pi v being a uniformizer v, then how do you capture the Iwahori subgroup? Well, Iwahori subgroup would be the pre-image of the Borel subgroup over the residual field. Okay, so outside of some finite set, you will have this is smooth. Moreover, this embedding will be a close embedding of a smooth group scheme. So when you reduce mod pi v, you are going to get an embedding over of reductive groups over this finite residual field. Okay, you take a Borel that intersect. Similarly, this Borel will intersect. So all these statements behave well with respect to reduction mod pi v outside some finite set. So you can arrange this and also similarly the IV minus, which is intersect the lower triangular same thing. Okay. I want the same thing. Something in here. Okay, because I just have one more condition, which is that I want this n to be smooth over OV and pi v to be trivial on n. Okay, as before, the smoothness will hold outside some finite set, and this is because chi is a smooth character. Okay, it's a smooth character, so it's trivial on some open compact subgroup of NA. An open compact subgroup of NA almost everywhere will be this thing. All right. Okay. As I mentioned, if you are willing to take H to be SLN, then I don't think I'm saying anything at all here. Okay, now I'm going to fix two finite sets of places. Which are disjoint, okay, and disjoint from so this S1, S2 are the so-called good places where I have those properties. Now I'm going to describe the construction of a compact of an open compact subset of HA. Okay, because I think I mentioned last time the way I'm going to construct this globalization is by Poincare series. Okay, so Poincare series I have to take a function on HA which is smooth and of compact support. Now, the reason why I'm trying to construct an open compact subset is, roughly speaking, I want to take a characteristic function of this open compact subset later on. Okay. Okay. So what is so suppose I'm given C S0 and a fixed open compact subset of H. E. Suppose I'm given this. Now I want to define an open compact subset for all other V's and then put them together. Okay, so I have to tell you, so I want to define or construct CV for all V not in S0. Yeah, do it over here. Okay, so let's see. Let me start with the easiest one. Okay, so for all V not in T, which is S union S0, union S1, union S2, because I have fixed all these sets here, right? I'm going to take CV to be this hyperspecial maximum compact. I already know in S0, so I have 3 sets to tell you. For all V in S1, I'm going to, actually let's do S2 first. Okay. S2, let's take CV to be IV minus. So maybe I didn't say what the Iwo-Hori subgroup is of GLN, right? So it is those matrices which are, so these are, so they are matrices G which are congruent to mod so that's what the upper triangular Iwo-Hori subgroup of GLN consists of n by n matrices in GLN OV with integer entries, such that when you reduce modulo the uniformizer, you get an upper triangular matrix. Okay, and similarly for the lower triangular, it will be the lower. Now for all V in S1, I'm going to call it JV plus. This is the Rho P C-log or Rho P C-log of IV plus. Okay, so what is that? Well, so I already told you this is IV plus, right? All the n by n integer matrices whose reduction mod pi V is upper triangular. Okay, now of course this is a Borel subgroup of GLN over the finite field, and you can look at its unipotent radical, which are all things like that. Okay, this is a P group. Okay, and when I take the pre-image of this in here, that will be this Rho P C-log. In other words, the maximum Rho P, normal Rho P subgroup. Here, maybe I say a couple more words. So I guess, so if you look at GLN, OV, of course you have the reduction mod. You know, mod V, and you get some finite field. So I don't know. And okay, there's a reduction mod pi. Right? And over here you have this Borel subgroup, which is this upper triangular matrices over the finite field. The pre-image is will be this IV plus in the context of GLN. Okay? But now, if I take this U of FQV, which is this unipotent matrices, okay? This is a P group. And when I take the pre-image, this is for the Rho P. Okay? The reason is because when you take this mod this, of course it's just the same as this mod that, and you're just, the quotient is going to be just the torus, which is a prime to P. Okay? The order is prime to P. So that this is the largest P subgroup of this Iwo-Hori subgroup. And it is a normal subgroup. Okay, so, right? Okay, and finally, for all other V, so for V in S, I'm going to let CV be any Iwo-Hori subgroup such that the character chi V on CV is trivial. Now, why is that possible? Why does such a unipotent subgroup exist? Well, okay, as I said, we are looking at two special cases, right? If n were trivial, there will be no condition here because it's automatic. Okay, if n were the unipotent radical of the Borel, okay, then you see. So of course, we also have this standard Iwo-Hori subgroup here, and your character may not be trivial on it. But what happens is you can conjugate this by a diagonal element, okay? And when you conjugate it, like over here, by an element like this, okay, let's say GL3, right? You take a torus element, you conjugate this, then what happens to the entries? Well, the entries up here will get multiplied by something like this. Right? Now, you can choose the A1, A2, A3 so that these numbers are, the absolute value is as small as you like. Okay? This is going to contract this upper triangular part into a smaller and smaller neighborhood of the identity. Okay? So, if you make it small enough, you can ensure the character is trivial. But of course, this is just a conjugate of an Iwo-Hori subgroup. It's just another Iwo-Hori subgroup. Okay? So you can always arrange this. Okay, so now I have defined for every V an open compact subset. Okay? And at S0, it is just any given one. But at all other V's, you know, actually I've taken some open compact subgroup. Okay, and here is the key lemma.
Maybe you have to restrict chi V to the intersection of CV and N.
Yes, that's right. Yes, that's right. That's what I mean. So N intersect CD. Yeah. Thank you.
And the intersection you contain in a zero subgroup.
This intersection, I just want to say that I can make this intersection very, very small.
Yeah.
As long as it's sufficiently small, the character will be trivial on it because it's a smooth character. Okay. All right. So here's the lemma. The lemma is if S1 and S2 are sufficiently large, then HK intersect C. Okay, so C is this open compact subset that I've constructed. Yeah, so it is contained in NK. For 1 second, okay. Yeah, okay. I'll do that, okay. So just recall that I'm assuming that N is either trivial or U, okay? And if N is trivial, I need to take both of these sufficiently large. But if N is U, I think I can just suppress this one. But as you'll see, the proof is not hard, okay? Now, of course, we know this is a finite set to begin with. Because this is discrete, this is compact. So what is the the proof. So you take, let's take any element gamma in this intersection. Okay, remember, gamma is an n by n matrix. Okay? And so it has n square entries. Right? And those entries, this coordinate function, right? Which is a function field of y, of a curve y. Okay? So this xij gamma are functions on y. I should write FQ. It's a curve over finite field. Okay, so let me see what we are doing here. Okay, so I want to examine the behavior of these functions, okay, at each close point of y. Okay, or each place of y. Okay? Now, so let's see, for all v not in T, remember T is this S union S naught union S1 union S2. You see all this, if gamma were in this intersection, right, so this product of V not in T, C, V is just product V not in T of H of OV. Okay? So this implies that for all ij, xij of gamma, I inside OV, okay? i.e., it has no poles at V in close point, V not in T. So we have this n square rational function on a curve, and we know that outside of this finite set T, it is regular, okay? There's no pole. Now, if you are in here, okay, so you see at S naught, you're just given, you had a fixed open compact, okay? Now, so this means that the V-adic valuation of each of these is going to be bounded. Okay? So there's some bounded order of poles. Okay? So there is some M, okay, such that for all ij and for all v, the order of poles of xij gamma is less than m. This is for all gamma in that in that finite set of so in this. Now, what about V in let's say, as well, for V in S1, this CV is by construction JV plus, right? So this means that if gamma is in here, then for all, so in the upper triangular part, sorry, on the lower triangular part, so this means I bigger than J, xij gamma is congruent to 0 mod this, right? In other words, xij gamma vanishes at all v in S1, okay? which is a subset of close points. And for all I, II gamma minus 1 vanishes at all v in S1. Likewise, at the places V in S2, CV is IV minus, so this implies that, just like before, but now it is for the upper triangular part, Xij gamma vanishes at all V in S2. Okay. Now you see, if you make S1 sufficiently large, then you see that these entries for I bigger than j, which are the lower triangular entries, they will vanish to, they will have at least the cardinality of S1, number of zeros. Okay? So if you make this S1 very, very big, in the end, you are going to have more zeros than poles, right? Because you know that outside of this finite set, there's no pole. The only poles, are possibly in these places, and each one of them there's some finite order, some upper bound, okay, which depends on the compact subset you have already chosen at those places. Okay? So now when you increase this S1, when S1 is sufficiently large, this will have more zeros than poles, and that's not possible, right? Because principal divisors should have the same number of zeros and as their poles. Right? I mean, rational functions should have the same number of zeros as poles. Or put it another way, by the product formula. Okay. So when S1 is, the size of S1 is sufficiently large, you see that this thing has to be just a zero function, okay, it has to be 0 for all I bigger than j, and xii of gamma is just a constant function 1 for all I. So if your group N is just a unipotent radical of Borel, then you are already done, right? You don't need this S2 at all, okay? Because this implies that this intersect C is contained in U. Okay. On the other hand, if you let S2 also be sufficiently large, then you get the constraints on the upper triangular part. So this thing will be 0 for all I less than j. Okay? And this together, taken together, will tell you that HK intersect C is just 1 point. Okay? So you see that if you think back to that trivial observation at the beginning, where I said there were 2 ways of showing that an integer in some bounded interval is 0, right? And clearly, I'm using the second way, which is to show that that integer is divisible by sufficiently many primes. Okay? Whereas in my last lecture, when I talk about showing that a Poincare series is non-zero, I use this stringing support argument at one place. Okay? And that is using that first observation, showing that it is divisible by sufficiently many powers of a given prime. Okay? All right, so depending on which case you are in, I mean, if n is u, you don't need h2, you already get the lemma. If n is trivial, you use s1 and s2, and you get this. Okay. So now I can construct a test function f from which I'm going to build a Poincare series. Any question? Okay, so construction coefficient. Okay. Now, for all V naught in S naught, I have a supercuspidal, right? So I'm going to let F V naught be a matrix coefficient of pi V naught, right? In the theorem, I have a given supercuspidal, such that, so I think I mentioned also last time, one equivalent way of saying a supercuspidal is that the matrix coefficient is compactly supported, modulo center. Okay? But I'm assuming the group is semi-simple, so the center is not an issue. Okay? So I would like non-zero. Now, why does this exist? Well, this is because we are assuming that, so remember that in the theorem we are assuming that this pi V naught is chi distinguished, right? We know this is not zero. I.e., we are assuming that the twisted Jacquet module, say this, so this is, this twisted Jacquet module is not zero. So what is this space? This space is pi V naught modulo the span of vectors that, okay? So it's the maximal quotient on which n acts by this character. I'm trying to explain why you can find a matrix coefficient with this property. Okay, so in any case, so this means that because this space is not zero, and this is just this quotient, right? So this means that there exists a vector f, okay, in pi V naught, such that f is not in the kernel of the projection map from here to, like that. But one has an alternative description of this kernel, okay? So this kernel are all those, I'm running out of, I don't want to use V, so let me just say W in pi V naught, such that integral is zero. Okay, so where's this integral happening? Well, I want to write n, but the integral may not converge. So let me just write for some sufficiently large open compact, let's say subset omega of n. Okay. So there's this, so of course we know what the kernel of this projection is. They are all vectors that look like that. But there's an alternative characterization given in this way. Okay, so, but we have a f which is not in the kernel. So this means that we have a f such that this integral is not zero for all sufficiently large omega. Okay. Then, okay, so for all sort of omega, let's say, for all sufficiently large omega, this is not zero. Now, whatever this is, right, this is just another element inside inside the representation. Okay, so there exists f check in the dual representation such that the pairing between this and this non-zero vector is not zero. So if you bring this pairing inside, what you have will be a matrix coefficient. So meaning will be non-zero. Okay, so I will have this. Okay, now of course if I'm in the case when n is trivial, then there's nothing to assume here. Okay, and let me assume that no, sorry. So if n is trivial, then all I'm assuming here is that fv0 doesn't vanish at 1. That's all. Now that I have chosen this matrix coefficient, which is a compactly supported function on H, so I'm going to set C V0 to be the support of FV0. Okay, this is for V0 in S0. Okay, so that defines a compact subset at the places in S0, and by the earlier construction of this compact set. So now I'm going to say for all V not in S0, I will take Fv to be the characteristic function of Cv. So Cv is constructed before. Okay, when I constructed this compact set, see, I had to assume first I take a CS0, right? Okay, but now I have fixed my CS0. After I chose this matrix coefficient, I take its support. That determines CS0. And then I do that construction. I get some Cv. I take the characteristic function. Okay. Now consider this Poincare series. Pf of H is averaging over the group to make it HK invariant on the left. So the claim is, so I want to show that this, I mean, firstly it's not zero, right? But in fact, I will show that when you compute this, this thing is not zero. Of course, then it will show that it is not zero, but in addition, it will have this globally n-chi distinguished property. Okay, so why is that? So that's the computation. You put in the definition. This is compact, so this integration is a harmless thing. Okay. Now, okay, so now in this integral, when we sum over this, okay, you see it suffices to sum over now I remember what I missed out in that, but I mean, there's an n here, right? So I should do something like that. But okay, so I guess now I realize I missed out something earlier. So because okay, so for example, if let's pretend n is trivial, because I say I'm keeping these two examples in mind. If n were trivial, of course there's no integral. I'm just evaluating pf at 1. Okay, I would just have this sum. Okay, but there will be no n. Okay, it's just f gamma. I want to show that this is not 0, right? But by this key lemma, right, when I make S1 and S2 sufficiently large, the intersection will be just the identity element. Okay? And so since my function is non-vanishing at 1, by construction, it is not 0. Okay? Now, if I have this, if n equals to u, let's say, okay, then it's still okay. It's just that I would have to, what I have to do is I have to choose a compact subgroup of NA that projects surjectively onto this quotient. Okay? This exists because this is in the function field K, so this has arbitrarily large compact subgroup. So I'll pick a compact subgroup of NA that projects surjectively onto this. Okay? Call that Cn, let's say. So I pick some Cn, which is compact. Here, then over here, I would have to probably do this. Now, this doesn't affect the argument so much because basically at the places in S0 and S, it is just some, you know, you still have this, okay? It is just some compact subset, so you have some bound M, which controls the possible sizes of poles. But at the other places, once you are outside of S, this Cn, yeah, so I should say when you choose your S, you want to make sure that for all V not in S, union S0, CNV is just N of OV. Okay, so in other words, for the places V outside of S union S0, putting this Cn there doesn't really do anything. It's already in C, I guess. Okay, so I forgot to put it in. So the reason is because here I need, you know, so maybe I put something like that. But it is a group, so support of F is this C. Okay? And by the lemma, we know this thing is in NK. So this is by the lemma. So this means that instead of writing sum over HK, I can just sum over gamma in NK. Then I can collapse the integral with the sum, okay? And I will get just this. And let me see. By construction, this is non-zero. Okay? Because of course this is a product of local integrals. At a place in S0, that's what we have arranged. We pick a matrix coefficient so that there is not 0. And outside of there, our function is just characteristic function of this CV. And this CV is chosen so that chi V is trivial on N intersects CV. Okay, so there will actually be no chi at those outside of S0. And what you are integrating is just a characteristic function of CV over N. So you just get the volume of CV intersect NV, which is not 0. Okay, so what have we done? Just to summarize before we take a break. So I have produced PF. Well, it's a cuspidal function. Okay, because I think I explained this last time, because you are taking matrix coefficient of a supercuspidal at some places. So what you get will be a function with 0 constant term. So it's cuspidal function, which is n chi distinguished. Now, such a cuspidal function will live in L2 of, in fact, it's compactly supported. So you will live inside this L2 space. So you can consider the HA submodule generated by this vector. Okay? Now you let pi be an irreducible summand in, right? So this you look at some you have this function. You look at the HA's submodule generated by this function. Okay? Then you're going to get some subspace of the space of cups forms, right? And that space is a semi-simple. Okay, the space of cups form is a semi-simple representation. You'll break into pieces, so you just take any irreducible summand. Okay, and this guy will work. Okay, so this gives the pi in the theorem. Well, have we checked all the conditions? Well, it will be the case that at places in S0, this pi V0 is just the given supercuspidal because you use a matrix coefficient. Okay? Now, so the only condition that is left to check is that at the places not in S0, I want to make sure this thing is a principal series induced on the Borel. Now, why is that? Well, the reason is because this function, because I take at the places not in S0, this guy is what is this? It is always some open compact subgroup. Okay, it is either at almost all places. Of course, it has no choice. It has to be this hyperspecial. But at some places, for maybe S1, I mean, it is JV plus, right? And other places, it is IV minus. Something like that. Okay, so at a place where it is this, your representation will have a non-zero vector fixed by this maximal compact. So you'll be unramified. At the places where you have this, you will have a non-zero vector because this PF will have this PF has non-zero projection here because this is a summand in the submodule generated by PF. So it has non-zero projection, right? So that projection will, at the places in S2, will have a non-zero vector fixed by an Iwo-Hori subgroup. Okay, so then I guess it has been known by Borel that such a representation is contained in an unramified principal series induced on the Borel subgroup. What about here? Well, this is a slightly smaller subgroup, right? It's the pro-P radical of an Iwo-Hori subgroup. Well, by results of Moy and Prasad, and also Lawrence Morris, one knows that if you have a representation which has a non-zero vector fixed by this pro-P Iwo-Hori, then in fact it is also induced from the Borel, but by a tamely ramified character. Okay? So in all cases, you know that outside of the place S0, your representation will be induced from the Borel subgroup, but from at most tamely ramified character. Okay? And that proves the theorem. So I maybe take a 5-10 minute break. Yeah. sorry, the first part was quite maybe a bit technical because I talked about the proof in some detail. Now I want to remind you of a corollary. So let me state the corollary. So in this corollary, you are given only local data. There's no global anything at all. And then, but in order to apply the previous theorem, you have to start to globalize some of the things. Okay? So you are given F, a local field of characteristic T bigger than 0. You are given, so this is one thing. Now you are given, so the similar data as in the theorem, a connected reductive group whose connected center is ZF. And let's say it contains a parabolic subgroup. Okay. Have a unitary character on the unipotent radical, and but I want to assume that that it lies in an open MF orbit. I'll make a comment about what this means in a moment. And you are given pi 1 to pi a supercuspidal representations, irreducible, of HF with the same, just emphasize same, central character under ZF. So maybe let's say ZF character, omega. And let's assume that it is NF chi F distinguished in the same sense as the. Okay, so you are basically given this data, but everything is local here. But of course, it is slightly more restrictive, right, than in the theorem because I don't take N to be any unipotent subgroup, right, but only the unipotent radical of a Borel, of a parabolic subgroup. Now. So this is over, everything is defined over F. Okay. Then, I want to say there exists global field K with places V1 to VA such that they globalize that local field F. And we have this picture globalizing that. Okay. At all VI. Now I have to globalize the character, right? Unitary character such that, okay, so of course, you know, maybe you think that what I would like to say here is that chi of VI is equal to chi F. Okay, I could not quite, one could not quite say that because, you see, the reason is because if you just give me an arbitrary character, there's no reason why it can be globalized to a global character. So for example, suppose you take N to be just the additive group GA, right? And you have some number field K, or some global field K. So you're looking at, so you're saying, well, can I find an additive character of A mod K whose V component is some given guy? And the answer is no, that cannot always be done. Okay? But you can, so that's why I need this open. Okay, so to ensure that this thing and this guy are in same MF orbit. I'm going to make a comment in a moment. And finally, the cuspidal representation pi of HA as in the theorem, meaning it will globalize the given supercuspidal. It will be n-chi, globally n-chi distinguished, and at places outside V1 to VA, it will be in this principal series induced from minimal parabolic. Okay, so you see that this is a corollary of the theorem. That means that we are going to apply the theorem. But before you apply the theorem, you have to globalize these things, right? Because in the main theorem, almost all data that you start with are global except for these supercuspidals. Okay, so you have to globalize and find these things first on this board before you can apply the theorem. Okay, and that's what mainly I want to discuss. Okay, but okay, so let me make a remark about this open MF orbit condition. Okay. So note that if you consider the group of algebraic group homomorphisms from N to GA, let's call this V. So it's just an affine K space, affine space over so maybe I should just start with F first because affine space over F. Let's call this F. Now, if you fix so if one fixes a character, a non-trivial character, phi F, then, of course, by composition with psi, you get a map from, so you get bijection from home, just from VF to just unitary characters I didn't, I suppressed the F points here. Right, how? Because if you give me some F here, I will just do, so you get a bijection. Okay, so I think the point of this is to say that this set of unitary characters has a natural structure of an affine F space. Okay, but the identification depends on the fixing some additive character, non-trivial additive character. Okay, so and this bijection is MF equivariant. Because the M normalized N, right? So it acts naturally on this set. It also acts naturally on that set. So this explains the condition lying in an open MF orbit, because if I regard this, so my given chi F would be an element here, right? But which I can think of as an element there. Okay, and so I have an affine space with an MF action, and I would require its orbit to be Zariski open. But then it means that, because this is a vector space over F of some finite dimension, so of course it has a analytic topology, right? Because F is a local field, and by requiring that orbit is Zariski open, then it will also be open in the analytic topology. Now, so you have the same discussion over, so if you have a global field, you will have the same, and you fix, let's say you fix a character of this non-trivial character. Okay, then, similarly, you are going to get a bijection from VK, which is home N to GA. meaning assuming you are in a global situation, okay, so you have from NA or NK to S1 in the same way. So you have F. Okay, so the set of this thing is a finite dimensional K vector space. Okay, and of course, here you can take the so let's say you have a place V, okay, so if you have a global character, you take the V component, so you have this localization map, and it will just correspond to the natural inclusion of this vector space to that one. All right. Hence, you see, because this map is not surjective, right? So this means that if you give me any character here, which means a vector in this KV vector space, there's no reason why it's in the image. Okay? But if it lies in an open MV orbit, right, then the MV orbit is an open set inside this vector space, and this inclusion is dense. So you can find a K value, K rational point in that open set. Okay, and that will be a global character. That well, you will not necessarily globalize your given guy, but it lies in the same MF orbit. Okay? So I think the point is to say that, to explain what that open MF orbit condition is, and to say that, well, once you have globalized the things above, to find this character, it's just this argument. All right, so now our point is to globalize the field, the groups, and so on. So let's do it in stages, globalizing local fields. Okay. Of course, it's very easy if you want to globalize a local function field, right? Because we know that every local function field is, isomorphic to a Laurent series in one variable over finite field. So of course, then you can say, let me take K naught to be this global function field. Right? This is the function field of T1. Okay, so it's very easy. Okay. However, actually, I did something more. I need a certain the following lemma. Given finite Galois extension, E over F of local fields, I can find finite Galois extension. Let's say K1, K prime over K. With a place V such that so KV is F and K prime answer KV is E, okay, and such that the degree of the extension is the same. Okay, of course, this will force this place. So V, the place V in K is inert. In K prime, and the Galois group of K prime over K, well, the local Galois group will sit in there as a decomposition group, right? But it will be isomorphic because the degree are the same. So. Okay, so anyhow, it was not immediately clear to, so the proof is by Krasner's lemma. So in other words, it's not a sophisticated thing. Let's leave it as exercise. What is not clear to me was like if you have this and let's say you start with K naught with a place V such that K naught of V is F, then can you then build a can you take F to be, no, not F, the K to be K naught, let's say, and then build a K prime? That's not immediately clear to me, but I don't need it. So I'm happy to find some K for which it works. Okay, maybe if you use more machinery, like local class field theory, you might be able to do this globalization with a given K. Okay? But I don't. I have the flexibility to choose K. But I use very little, just this. You'll see in a moment why I use this lemma. Okay, so now I want to globalizing the groups with the parabolic subgroup. So in application, so this parabolic subgroup could be the whole group G itself, right? So meaning, the n could be trivial. Okay, so this could be equal. Okay, so the two cases to keep in mind is one of them is when it is equal, so that means I suppress it, or when it is a Borel subgroup. So that this n is the unipotent radical of Borel. Okay, anyhow, so let me first assume first that HF is a quasi-split. Okay. Well, we know what quasi-split groups are. So quasi-split. Okay. Okay. So the key starting point ingredient is that we take for granted is of course, the well-known theorem of Chavalet that there is always a split group. Given any reductive group over, say, an algebraically closed field, there is a split group defined over Z, whose base change to that algebraically closed field is isomorphic to your given one. Okay? So there is a split group HS over Z F bar, let's say. Right, so that's of the same type, okay? Now, so you take this split group, okay, then we know that the quasi-split groups over F, which are isomorphic, to HS over F bar is in bijection with Galois cohomology sets. Taking values in outer automorphism of HS. Now, your HS is defined over Z, so this thing is also defined over Z, and in fact, it's a constant group scheme. Which means that you take endpoints anywhere, it looks the same, essentially. Okay? So you have that. Now, so we have our HF, right? Our HF is an element here. Is isomorphism class is an element here. So it corresponds to some cocycle, some cohomology class, which may be represented by some cocycle. Okay? Moreover, if E over F is a finite Galois extension such that HF splits, then you can take this cocycle. You see, because this Galois cohomology set is defined as the inductive limit of H1 of Galois E over F, right, over all finite X Galois extension. So if you have any class in here, in fact, it lives inside some H1 of some finite Galois extension. So there's some one cocycle like that, which you can use to twist the Galois action on the split group and to define your HF. Okay, now I'm going to use the lemma, by this lemma about globalizing local fields. Okay, you have K prime over K, global, extension of global fields, such that you have that. So by composition of this isomorphism with this map, you get a one cocycle. So you're going to get a one cocycle over K okay, so you are going to get some class in here. And this, so that will be this will give a quasi-split group H over K such that H of KV is HF. But in the lemma, we have some place, right, that localize to F, E, and whatnot. Okay, now how about the parabolic? Well, you see, parabolic subgroups of quasi-split group is very easy to describe because, in fact, let me do it over here. You see, because everything can be described by yeah, so I guess maybe I say so. So if you have this split group, of course you have the base root datum. So let's say you pick a Borel subgroup. Okay, then you have the usual base root datum, right? Which is character group. You have the torus, the simple roots for P, and you have the co-character, and so on. With the base root datum. Now, if you have a quasi-split group, so you have this cohomology class and this cocycle, then you get HF, you're going to get this, okay, so you have this HCF, right? And this HCF is going to give you a twisted Galois action on this base root datum. So for example, you will permute the set of simple roots. Right? That's why we look at quasi-split group, you have this diagram automorphism. Okay? Now, and the parabolic subgroups are determined by orbits of this Galois group on the set of simple roots. Okay? So Gal E over F orbits on this delta correspond to maximal parabolics. Okay, so maybe I say subset of a set whose elements are the Galois orbits. Okay, so you know what the parabolics are because you know, the Galois group acts on the simple roots or the Dinh-Kien diagram if you wish. And then if you take any Galois orbit, that gives you maximal parabolic defined over F. Right? And you take a bunch of several Galois orbits, and if you take all the whole, then you just get the Borel subgroup. Okay? Now, so you can read off what the parabolics are just from this combinatorial data with this group action. But now when we define this global group, right, everything is based on this isomorphism. So the action of, when you have this group over K, its associated Galois action on this base root data is the same as the local one, okay? Under the isomorphism from the natural isomorphism to Galois group. So you see that the parabolics are just described by the same thing, by the same combinatorial data. So there's a one-to-one correspondence between the parabolics of HF and the parabolic of this H that we have constructed. Okay, so that's the case of quasi-split, which in fact suffices for my application, which, as I said, because my application was either N is trivial or it's a unipotent radical of Borel, which means that my group is a quasi-split. But let's consider the general case. Okay, so let's consider now a general case. I see. I forgot to say one thing. In this globalization here, I forgot to say one property that I want, which is this Z. I would like globalizing this and such that, so let me say, such that the K rank of Z is equal to the F rank of ZF. Okay. You will see in a moment why I need this. Okay. So for example, suppose that this ZF is a one-dimension split torus. So it's GM. Right? It's just split. Now when you globalize, of course you can take an anisotropic one-dimension torus that globalize it. But I don't want to do that. Okay? So I want to take something with the same rank. Right? So if this guy is a rank, if the F rank is 2, I want the K rank of Z to be 2. I don't want to make it more compact. I want to maintain the same degree of the splitting degree or whatever you call it. Okay. I forgot to say that. Now, and over here, do I have that? Well, yes, because again, the F rank of ZF is something you can read off from the Galois action on the co-character or the character group of the torus, or the co-character group, right? Because the co-character of ZF, because whatever ZF is, right? Z is a subgroup of the torus. Okay? So the co-character, I mean the center of HF, which is also the center of this split group HS. Right? So if you look at the split group, I mean its connected center ZS is going to be a subtorus of TS. So the co-character group is a sublattice, which is stable under the Galois action. And what is the F rank? The F rank is the, if you work over Q, if you tensor this Z lattice with Q, it's just a dimension of a fixed space by the Galois action. Okay? But since our Galois module is the same under the isomorphism, then that doesn't change. That doesn't change the split rank of the center. So in the quasi-split case, you see that the main reason is just that because the structure theory of quasi-split group, almost everything can be read off from the Galois action on the base root datum of its split form. So if you manage to globalize in such a way that this Galois module is the same, then all the things will be okay. All right, now let's come to the general. General case. Okay, so given HF, okay, so now it might not be it's not a quasi-split form anymore, but you can let this thing be its quasi-split inner form. I mean, you still have the split form HS, okay, as before. Okay, then by what we have just done, we have found a few K, and we have found a H prime over K, you know, globalizing. So I should say, okay, there's this parabolic, okay, but there will be a corresponding parabolic on the quasi-split form. Because somehow the, if you have an inner form of a quasi-split group, it has less parabolics than the quasi-split form. Okay, so every parabolic of the inner form is there is a corresponding parabolic for the quasi-split form. So now we have already found this, right? Globalizing. Okay, this is by the case just now. Okay, and such that the center, you know, the rank works out correctly. Okay, all right. Now let's see. Suppose we just forget the parabolic at a moment, and we just want to globalize this group. Okay. How do we do that? Okay, so this group is going to give a certain class in H1 of F of the inner automorphism of H prime F. Right? This inner automorphism is nothing but the adjoint group. Sorry, a lot of the subscripts. What we are asking, in other words, so we need to show that the natural map, the natural localization map from H1 K of H prime adjoint to H1 of F. So F is a KV, right? Of H adjoint, okay, is surjective. But if we know this, then we are good, right? Because then we can produce an inner form which globalize this HF, because so HF give it's a class here. So if it's surjective, I find something there that maps to it. Okay, then I'll have found an inner form of H prime over K that localize to my HF. Okay, so this is actually a theorem that this thing is surjective. So in characteristic 0, this is a theorem of Borel and Harder. This is in a paper, I think 78 credit. Okay. Of course, they can work with a finite set of places, not just one. Okay, if you have a finite set of places, you have mapped to the direct sum of H1 over KV. As V runs over S, it is surjective. And so in characteristic P bigger than 0, so basically the argument have been extended by, let me see, Q. Yeah. By Tang. Okay, Tang and Han. This is maybe within the last 10, 15 years. Okay, so I mean the upshot is that you you can globalize this group HF to a group over the global field. Okay, but now you want to also globalize the parabolic, right? Not just the okay. So, but for us, we need to consider not just the inner automorphism group of H prime, but the inner automorphism group of the pair. If you want to use the Galois cohomology, you will be looking at inner automorphisms of H prime that preserve this P prime. But of course, a parabolic is self-normalizing. So this thing is just P prime adjoint. P prime adjoint just means the parabolic subgroup that you obtain from P prime by projecting it to the adjoint group of H prime. Okay? So what we need is we need the surjectivity of H1 K to H1 F but of course, it is not hard to see that this is just controlled by the levy, okay, because the n unipotent radical of parabolic is k split, so it's successive extension of GA, so there's no cohomology. Okay, now this M prime is a reductive group. Okay, so I mean, basically, you want to reduce this result, but this result is it works for semi-simple groups. So you have to do a little bit or more work with these are reductive groups, right? They are Levy subgroups of some semi-simple group. Okay, but because it is a semi-simple group, but you see that if you look at M prime, this looks bad. Look at the, it's not reductive group, you can look at the derived group. Okay, the derived group, of course, sits inside here, and the quotient A is a split torus. Why? It's because, you see, this is a levy in this adjoint group. Okay, there's no center, okay, the group has no center, so when you take a levy, you just acquire some split torus. Something with H1 is trivial. So now this is going to lead to the following diagram. Sorry, that's a derive. So it's going to go to this H1 of A, but this is a 0 because it's a split torus. Okay. Similarly, over F, okay, so what are we saying? We are saying that this map is surjective. These two maps, horizontal maps, are surjective because of the 0. This is a semi-simple group. So by those theorems, this is surjective. So this forces this to be surjective. If you give me an element here, I leave it to there, I leave it to there, and whatever the element is, when they map here, they will be sent to the 1-to-1. So this forces the surjectivity. So that shows that you can, that's what we want to show. Okay, now, and the other thing is about this, the F rank and so on. you see, because this is an inner twist, so whenever you get this co-cycle value in the adjoint group, right? So you are just twisting the Galois action on H prime by an inner automorphism. And that doesn't do anything to the center, right? Inner automorphism commutes with the center. So it doesn't change the Galois action on the center at all. Right. Okay, so that finishes the proof of the corollary, because now I've globalized the field, the H and the P and the Z with the required properties. Okay, I already explained how you can globalize the character chi F, and then now you're in a position to apply the theorem. Now, why is it that I don't allow any unipotent subgroup? Because here I only look at unipotent radical of parabolic. Well, it's because I do not know if the following is true, that if you give me any unipotent group in some group over local field, so as we explained here, we can globalize this group over some number of fields. But I don't know if you can always globalize a unipotent subgroup over local field. But see, I know almost nothing about unipotent subgroups, except maybe unipotent radical of parabolics. I don't know what they look like in general. I don't know if they could be globalized. And that's the reason. Yeah. Okay, and maybe last 5 minutes I want to, I have not, there's still one other thing, right? I have to globalize this central character. Did I mention that in the corollary? I forgot if I mentioned that. I did mention that? Yeah. Okay. So okay, so the last thing is, so we have this ZF, right? And which we have globalized to Z in such a way that F rank of ZF is equal to K rank of Z. Okay. Now, I just conclude with the following lemma. So, actually, before I say that, let me say this first. Okay, so given this data and given a character omega V naught from K V naught V V naught, V of K V naught, which is this ZF F. There exists omega so of course I want let me call this omega F. Okay. Okay. Then I want omega to be trivial on some distinguished place V naught. So this T is non-empty, okay? Non-empty. Okay, so what is this? Sorry, this is a bad notation because this is the maximal compact, maximal bounded subgroup. Okay, that's what this 0 means. And this 1 here means is the maximal rho P subgroup. Okay. In other words, what I'm doing is I'm given a character at one place, and I want to globalize it, and such at all other places, I have some control on the ramification. Right? So, I can take T to be a singleton set. Okay, that's not a problem. I can take T to be a singleton set. This means that in fact, my character is unramified, so meaning it's trivial on a maximal compact at all places except maybe one. I mean, beyond the fixed place that you care about. But even at this place, the ramification is not so bad. Okay, now let me make a couple of remarks. I mean, the first is, why do I insist on this condition? Well, you see, if you don't have this type of condition, right, you cannot even globalize a local character. For example, let's take the case when this is a split GM, it's just GM. Okay? But suppose you globalize, instead of just taking GM, you globalize it to be an anisotropic torus. Okay? Now, when you look at GM, of course, it's just some F cross, right? F cross is basically OF cross Z. So you see that it is basically a compact group cross a discrete group. So what are its characters? Well, the character of a compact group is a discrete set. The character of this is a one-dimension continuous family. Right? Because you can send 1 to any element in S1. So the character of a local, of GM over local field, it has a discrete parameter and a continuous parameter. But suppose you globalize this to be a one-dimension anisotropic torus. Okay, then you're trying to find automorphic characters, right? Characters of ZA mod ZK. But that will be a compact group if it's anisotropic. Then, so the only characters it has is a discrete set. So just from cardinality reason, you see there's no way you can globalize a local character to a global automorphic one. And hence, you need to maintain this type of condition. Okay? Now, the other comment I want to make is that in the corollary, you see I have A places that I'm trying to globalize. But so far, I've just globalized one place. But this is okay, because once I globalize one place, so far, okay, then I will just take an extension of K so that this place V0 splits into A different ones. Okay? And then I will base change everything I find over there. Okay? That is why in the corollary, I insist that even though I have A places, this omega, is the central character is the same. Because I cannot really globalize two places in general. Because for example, suppose this is GM, and now you're smart, you decide to globalize using GM instead of an anisotropic one. So that, okay, but now suppose you're given two characters, meaning two places of K. So you have two characters. Okay. But now you find that you have two discrete parameters, two continuous one, because you have two places. But on the global, we look at GM, so you're just looking at the ideal class group. The norm one ideals is compact. The quotient is real numbers. So you see that the automorphic character is just discrete parameter plus one continuous one. So again, there's no way you can globalize two arbitrary characters. So that's why I insist it's the same one. So in fact, what I do is I globalize one place, and then I just find an extension that splits totally at that place, and I base change all the data over. Okay. Maybe I don't talk about the proof of this because it's 5 o'clock. So I think I will stop here for today.